oxidation of alcohols, right? So here we go. That's going to be kind of an interesting topic because it will provide us with a variety of products that we are going to make, right? So what's oxidation from the organic chemistry perspective? That's either the increase in the number of oxygens in the final product or decrease in the number of H's, right? Sometimes it can happen like all at the same time, right? Other times it's different. So, but basically that's what kind of like oxidation can be characterized by, right? Either decrease or it's going to be like you have less H's in the final molecule, right? And or you have more oxygens in the final molecule. That's what oxidation is about. So let's show the example, right? So because it's all about like drawing structures in organic chemistry. So here we go. So let's take a look at maybe 1-propanol, right? So we'll start with the primary alcohol oxidation because they will give us a little bit more like products than the oxidation of secondary alcohols, right? And let alone tertiary alcohols. So here we go. Let's take a look at this. So yeah, all right. So let's, for our kind of example, we'll consider 1-propanol, right? 1-propanol, so we'll be looking like this. And then it is oxidized. Let's say it undergoes the oxidation using the mild oxidizing agent. Mild oxidizing agent means that there's going to be not so much oxidation going on, right? But still it will happen. So MOA, mild oxidizing agent. So what's going to happen in the case of primary alcohols, if you apply a mild oxidizing agent, you are going to receive the so-called aldehyde, right? So what do I mean by this? So that's what I mean. So CH3, CH2 show the parts which are not touched, right? So, and then what's going to be touched is this CH2OH locus right here, right? So this will turn into the aldehyde functional group. The aldehyde functional group, you should be familiar with that in general, in terms of what it looks like, right? So because we're looking at this at our very first kind of like online lecture in this series. So what you're going to do is show the aldehyde from this. So see what happens, right? So you did not change the number of oxygens, but if you look at this locus versus this locus, right, you decrease the number of H's, which means that from the organic chemistry perspective, the oxidation manifested itself, right? So you removed H from this carbon, right? And then it turned from CH2 essentially to CH, right? Less H's. You removed H from this OH, and then you turn it into the just O, right? Oxygen. So that's it. You decrease the number of H's, which is aligned with the definition of oxidation, right? It's either the decrease in the number of H's or increase in the number of oxygens, right? Sometimes they can all happen together, sometimes either thing takes place, right? So now let's take a look at another example, right? That's when we apply. So we still just consider like 1-propanol because why not, right? So this is our 1-propanol here. Sorry, this is an ugly H. So now the difference is that we are trying to apply, this is our reaction arrow, strong oxidizing agent, SOA. So here we'll have a little bit different situation. We're going to make from this locus, this locus will be turned into the carboxylic acid functional group. Look, CH3, CH2, CO, OH. So you see here, like both oxidation principles happened, right? So we increased the number of oxygens in the final product, and we decreased also the number of H's, right? So you see, so from these basically this carbon, sorry, we removed 2 H's and then turn it to just the carbon, right? So then in this case, we kind of retained OH essentially, right? So, but we also added oxygen. So yeah. So like 1 oxygen, 2 oxygens, we increase the number of oxygens. 3 H's, 1 H, we decrease the number of H's. So like all the kind of like traits, right? So characteristic traits of oxidation took place here. So, and then you can try just like for your own practice, very quick practice that you can do, for example, when you are in the queue at like CVS or something like that, right? So just like think about some kind of alcohol. Let's say I'm going to give you like 1-hexanol, right? And then apply one reaction will be mild oxidizing agent. Second reaction will be take again same alcohol, 1-hexanol, and then apply strong oxidizing agent, and then just draw all the products, right? In the condensed form, line angle structure, right? So like whatever you like. As you see, you can open the entire kind of worms of practice in this case, right? Pretty exciting. So next oxidation alcohol, next oxidized alcohol will be a secondary alcohol, right? So they will be like a little bit different from primary alcohols, right? In terms of the oxidation. Well, yeah, actually quite different when we think about the products, right? So we will have only one product type when we oxidize some kind of secondary alcohol. Let's have 2-butanol, for example, right? So 2-butanol will look like this. So here, as you see, I can use a medley of various structures. So this is going to be line angle structure. And then I'm going to apply either a mild or strong oxidizing agent. It doesn't matter. So because you can only make one product type after the oxidation of a secondary alcohol, right? So here we go. So what's going to happen, right? So here you'll be able to obtain the following, right? So you'll be able to obtain the following alcohol, the following products, sorry. So that's going to be ketone, right? So you're going to, if we write out some atoms, you're going to remove H and H. So that's going to be, in essence, the oxidation definition, one of them, right? So the decrease in the number of hydrogens in the molecule, and then you're going to make your ketone, right? So these parts will stay the same, CH3, CH2, then this carbon loses H, this OH loses H, and then you are going to do something like that. Guess what is missing? The bond, right? So now you have proper situation unveiling. You have tetravalent carbon and you have divalent oxygen, and you made a ketone. It's going to be carbonyl, which has the attachment to the carbon and another carbon, right? So that's your ketone, all set. So you made a ketone. So if you look at the tertiary alcohols, if you apply a mild or strong oxidizing agent to them, there is going to be no reaction, right? So because you cannot like make potentially like a pentavalent carbon with carbonyl on it. So like not possible, right? So you can try, but you'll make a mistake. So just saying. So now moving on to the next thing, we are going to switch gears and then we'll take a look at a special topic, which is going to be about thiols. Now it is like a sulfur-containing compound. So imagine that you have an alcohol, right? So, but then all of a sudden you switch oxygen to sulfur, right? And then sulfur can be also divalent, an atom. So, and that's what we have in thiols. So, for example, we can have a thiol like that. So maybe we'll have some kind of like carbon chain, right? And then here we will have our carbon, this CH2 here, right? And then it's attached to an SH functional group, right? So this functional group, right, will be basically represented as a carbon SH connection, right? And then this will be known as a thiol. So thiol functional group. So that's what it looks like. Now it is kind of embedded into a specific compound. So what can we say about thiols? They are relatively non-polar because of the like bonds that are present in those molecules, and they can also participate in some exciting chemical reactions, right? So what could that be? For example, oxidation, right, of thiols will give us a disulfide. So what we need to do is start with our thiol. So let's just make a different one for now. So it's gonna be this one, right? Something like simpler. So we'll have a thiol, right? So count the carbons, 3 carbons. So now we're going to oxidize this very thiol and then see what happens, right? So we're going to use two molecules, by the way, right? Stoichiometrically to show the product, it's a disulfide. Di stands for two, right? So consequently, you are going to like guess that maybe like two molecules will participate in this chemical reaction. Oxidizing agent, right? And then you are going to make the SS bond. So basically, you are going to remove H from here and H from there. And then you will have your liberated electrons on S, and then they will be connected to make a covalent bond, right? So let's show the product. So 1, 2, 3. Now it's just going to be the matter of practice, right? So take any other two thiols and try to oxidize them, right? So that's what we can make. So if we use the same thiol molecules that undergo oxidation, right? So we'll make a symmetrical thiol, as we can see from here, right? So another situation could be, what if we have a thiol, two thiols which are different? They can also undergo oxidation, right? So let's maybe show some sort of thiol, which is going to be looking like this, right? It's going to be a cyclic thiol. So this is going to be CH2, 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 CH2. But now we have CH here with an SH group, right? And we're going to react it with another thiol, which is going to be looking like this, right? So maybe 4 carbons, right, in the chain. So under oxidizing conditions, we are going to remove H, and connect the two sulfur atoms. Observe. So that's it. That's your thiol. That's your disulfide, which was made from two different thiols. That's pretty much our variety of reactions of thiols, right? So disulfides in turn can be reduced, right? So as you could guess, right, if there is oxidation, then there is a possibility of reduction as well. So if we want to reduce them, so then we are going to make our thiols back, right? So yeah, basically, let's take a look at some examples, right? So maybe we'll have some kind of like aromatic disulfide, which is going to be looking like this. Which will also have the alkyl chain like so, 4 carbons, right? So we are going to apply the H, which stands for a reducing agent, right? So because we are just trying to introduce H's, right? So by definition, again, reduction is the decrease in the number of oxygens and or the increase in the number of hydrogens in the resulting molecule. So basically, we break this bond and we fortify each sulfur with an H. So just redraw everything, right? If you break the bond in the molecule, then you're going to have to deal with 2 pieces, which will be produced. 1, 2 plus, right? So just kind of like mix of chemicals will be made. 1, 2, 3, 4. That's it. So now you have 2 different thiols. If you have a symmetric one, then you will have 2 identical thiols, like as a result of this reduction, right? So that's what we have about the disulfides. So what else can they do? So there's another interesting reaction, right? So that's when we react a thiol molecule with a heavy metal, right? Such as mercury, for example. So what's going to happen there? So you will form the sulfur metal bonds, right? So let me show you that. So yeah, maybe you'll have some kind of like thiol, so which is going to be looking like this. Let's say it's going to be thiol, right? Aromatic. So you have carbon SH, right? Piece here. So that's your thiol functional group present, right? So now you're going to take 2 molecules of this kind, right? And we can also redraw them, right, as just 2 separate molecules, because the stoichiometric coefficient of 2 is just to save the time, essentially. So, and then here you go, right? So that's your reaction, right? So with Hg2 plus, for example, some kind of like divalent metal, basically, right? So with the 2 positive charge, essentially, it could be other heavy metals, such as lead, for example, Pb2 plus, in other words. So what's going to happen? So this will be removed and this will be removed, right? And then you kind of like put Hg in between the sulfurs. So as a result of this reaction, you are going to obtain the following molecule, right? So you'll put Hg in the middle, and you'll kind of show the bonds that protrude from this piece, right? So now from this metal. So you are going to like make the bonds. So here you have essentially kind of like free electron, right? And then another free electron. So this is going to be a little bit more complicated than just kind of a covalent bond, because this is going to be like a metal and a non-metal bond, which is going to be here having quite a complicated character, because oftentimes those bonds between metals and non-metals can have either ionic character. In some other cases, they might have the in-between character between the ionic and covalent character. So things like that. So basically, for now, we're just going to say there's going to be the metal-sulfur bond, right, will be formed. Since it is a two-charged, right, so double charge metal, so it will be able to form two bonds, right? So that's what we need to pay attention to. So sulfur will be able to form one more bond because it was kind of deprived of the hydrogen, right? So, but it retains the bond between the sulfur and the phenyl group in this case. That's it. That's your example, right? So maybe you will have, like, instead of phenyl here, you will have just say ethyl, right? So in this case, you are going to have one piece, which will be like phenyl, sulfur, Hg, and the other piece will be sulfur, and instead of ethyl, and here, if you have ethyl, then this phenyl will be switched to ethyl as well, right? So we can maybe show it real quick and just kind of like for the practice purposes, right? Let's say you have ethyl, right? So here you go. Just show it like that, CH2, CH3. Then, like on this side of the resultant molecule, what you're going to have is not a phenyl, but ethyl, right? So now everything kind of like checks out, right? So everything is very nicely balanced in these circumstances.